Record on this computer. It's too dark. Let's see. Okay. Okay, hello everyone. We are down to the last chapter. There could have been two more chapters. So ordinary differential equations and partial differential equations, but over the years, I've concluded that it is better to teach one subject well rather than two subjects in a mediocre way. So because there's a lot of material to cover, and if I want to try to cram everything down to the last 6 lectures, it's not going to serve the purpose. So I'd rather spend the time left on explaining ordinary differential equations. I know some of you are taking ODEs concurrently or have taken ODEs. So I'd like to see kind of some hands who has already taken ordinary differential equations. Okay. And I suppose in the math department, you did that here at the U. Okay. Who's concurrently taking ODEs? Okay. Who has not taken ODEs? Okay, you have not taken like a formal course in ordinary differential equations yet? You don't think so? Okay, but you know what an ODE is? Have you been differential? Okay, so you covered some of that. I remember I had a discussion with you a little bit about that. Okay, that's great. So I'm the chairperson of the engineering math committee here at the University of Utah, and I work regularly with the math department to try to improve our engineering math sequence. And one of the critical questions, and that's kind of been a challenge to figure out, is who should be teaching math subjects for engineers? Should it be the mathematicians? Should it be the engineers? Or should it be a very nerdy engineer who knows a lot of math, or very applied mathematician who knows a lot of engineering, right? Because the objectives of the math course is to prove existence and theorems and things like that, right? But the objective of the engineer is to know how to use the ODE to say, look, this ODE exists, I know it exists because I can look at it, right? And I can solve it. What can we do with it? And so, there's always been tug and pull with this, but I like, for this lecture, at least for the ODEs, I would like to teach you ODEs from a different perspective, from more of a, try to develop an intuitive sense of what differential equations are, because what applies to ODEs eventually is going to apply to PDEs, right? They're just multidimensional. So if you grasp the idea of ODEs very well, and kind of comprehend what they're accomplishing, you'll understand why they are so powerful, why they are ubiquitous in all engineering and physics practice, okay? So that's the first part of this course, probably spend a good lecture on this, is to revisit or visit for the first time the concept of what a differential equation is, why we need it, how to develop one. We look at developing a few together so that you're going to get an idea, like why do you have this rate of change, and positive and negative terms, what do those mean, etc. And then we'll get into solving those ODEs numerically. Okay, does that sound like a good plan? Right? Okay, because I want you to be on board and excited, because I'm very excited about this chapter. This is perhaps one of my favorite chapters. Besides regression, the regression chapter, this is one of my favorite chapters, but it's also the most consuming, both in terms of knowledge and effort, because at the end of this chapter, we're going to combine everything we learned so far: linear systems, nonlinear systems, and finite differences and numerical integration, all of those together by the end of the chapter. Okay. All right. So let's go over the learning objectives. I'm hoping that at the end of the chapter, you'll be able to define a differential equation, define and identify dependent and independent variables, coefficients, and the right-hand side of a differential equation. You kind of know that already because we've talked with nonlinear and linear equations about these things. Distinguish between a PDE, partial differential equation, and an ODE, like what is ordinary about an ODE and what is an inordinary, like what's the opposite, what is not ordinary about a PDE. Identify and classify ODEs, so first order, second order, initial value, boundary value problem, be able to kind of grasp and what they mean. And describe the meaning of terms in an ODE, create Python code to solve a single or a system of ODEs. So when I say Python code, this could be our own code that we develop or using built-in tools. And as you've noticed so far, I'm trying to tackle both, okay, so that you know what's built in Python, but you also know how to build kind of the internals of what's going on in Python. We'll use implicit and explicit finite difference methods to develop a numerical integration methodology for ODEs, and use finite difference methods to calculate also the numerical solution of a boundary value ODE. So we'll see one gives rise to a time marching problem, which could or could not have a system of equations. The second one always results in a system of equations, and we'll understand why that's the case. Identify when the right-hand side of a ODE is nonlinear and when to use a nonlinear solver, and calculate a numerical solution for an implicit method with a nonlinear right-hand side using Newton's method. That's kind of like way at the end of the chapter, and linearize a nonlinear source term for a boundary value problem. Okay, there's not going to be time to do a homework on these, but the slides have adequate examples and explanation of kind of how to do this for your future reference. Okay, all right. So I'll start with a question: what is a differential equation? Okay. Go on, form into groups. I know most of your names now, so if you don't want to put your name tag, that's okay. Okay, but I apologize beforehand if I do not recall your name and I ask you for it. Okay. Okay. What's a differential equation? This is an intercontinental group. Hello, friend. Welcome to our class. Yeah, absolutely. Welcome, welcome. What's your name? Phil. Phil, nice to meet you. Thank you, thank you. Hey, Kimball, do you want to work with Brooke or Michael and Kara and whatever? Or, it's okay if you don't have to. Okay, so what is a differential equation? Your grandma grabs the phone, it's like, hello, what are you doing today? I'm studying differential equations. Grandma, what is a differential equation? Kevin. On the same equation, okay? That's very accurate and correct. What else? Did you just Okay, so why do we have a function and its derivatives in an equation? Why on earth would we have that? Okay, that's also correct, Michael. Okay, also correct. Okay, so those answers are correct. Formally, a differential equation is just an equation with terms that involve the derivatives or rates of change. I want you to think about derivatives as rates of change of an unknown quantity. Be a function, could be something. It's a quantity you're trying to measure. A differential equation is an equation that contains terms that have derivatives and rates of change. Okay, now I want to start digging deeper, but first let me just give you an example. Like this is an steady state advection diffusion equation, and I'm going to use that to define quantities in a differential equation. So this is by definition a differential equation because it contains a quantity t and its second and first derivative. So by definition, this is a differential equation. Okay, now the quantity that is under the derivative is often called the dependent variable or the response variable. And the quantity on which we differentiate is called the independent variable. So in this case, this is space, x, location, or could be time as well. And things that multiply those derivatives are called coefficients or parameters that could be a function of the dependent variable. So k and u could be function of t. They could be function of x, or they could be constant. Okay, that's kind of the most general case. So this is just a differential equation, right? But then why? Why do we see this often in nature? More technically, I think it's easier to interpret nature. It turns out that it's easier to interpret nature with equations that involve derivatives rather than just equations that are going to give you an answer. So let's dig deeper into what that means. Okay, so I'm going to take you. Okay, so this is the statement I'm making here. It is often easier to describe natural laws and complex systems by finding relations between rates of change of things rather than the specific values of a certain quantity. So I'm going to take you on a long journey now to kind of elaborate on this point and why it is so important. And I think one of the best systems to study differential equations are population growth systems and population balance systems, because they're very easy to interpret intuitively, right? You have two organisms, they're multiplying, so they double or they triple, and you can derive all sorts of formulas based on that. Okay, so consider a population of a unicellular organisms called paramecium. This organism kind of self-divides and replicates and propagates. In this population, each individual divides once per day. Okay, so for each day, if you have 3, the next day you're going to have 6, right? And the next day you're going to have 12, and so on. Okay, so you kind of see how the growth, starting with 1 individual on the first day, then you're going to have 2, then you're going to have 4, then you're going to have 8, and so on. So you can see kind of how that grows. Okay, this is just a plot showing that. All right, so starting with a single paramecium, the initial population is 1. We're going to call that P0. And then after 1 day has passed, the total population P1 is 2 times P0. There's like 2 individuals in that population. After 2 days have passed, you get 2 times P1, right, which is 2 squared times P0. And then after n days have passed, what is the population of the paramecia, the plural of paramecium, the paramecia, after t days have passed? Okay, so after 1 day, you have 2P0. After 2 days, you have 4P0. After t days, how many paramecia do you have? Go ahead and run that calculation by hand. They're not eating each other. They're not dying. Okay, they are eternal beings, and they they reproduce forever. Okay, we're gonna get to a point where there's, they get saturated. Okay. All right, what is the formula for P after t days? So P1 is 2P0, P2 is 2 squared P0, P3 is, and PT is, pardon me, 2 to the power t P0. That's correct, right? Okay, so after t days have passed, you can just derive this by recurrence, pretty simple formula. Every time you multiply by 2, so after t days have passed, you get 2 to the power t times the initial population. Now, I put here P0 because P0 could be 20 individuals or 1,000 or 1, right? And so it doesn't matter. It's just an initial population, okay? Now, in general, the rate of growth could be any number R. It could be 1.3, could be 1.7, which would account potentially for some organisms saying, I don't want to replicate. I just want to be myself, right? I don't want to replicate. Some organisms, so on average, that rate of growth is not necessarily true. It's just some number, because this idea, we want to eventually take it and apply it to other organisms in nature. Could be rabbits, foxes, wolves, whatever, any other population. Just to remind you, this is not a course on zoology or anything like that. I'm just using this example to illustrate the point of why we need differential equations. And if you just bear with me, and we'll laugh a little bit along the way, but if you bear with me, in the end, there is a very important point that I'm going to make. Okay, so take lobsters, for example. They reproduce at a different rate, right, than the paramecium. They have to meet each other, they have to get married and, reproduce and things like that. So, in general, after T days have passed, okay, you can express any kind of population growth as, the population after T days have passed as some growth rate R to the power T times the initial population. R to the R is an intrinsic property of the population at hand that can be observed and measured. So you go measure a population of sardines, for example, a population of wolves, and you have that number, okay? Now, I just want to do a little transformation here, because rather than doing powers for R to the power T, I'd rather write everything in terms of exponentials. So we can convert that formula to P0 times e to the RT, where e to the R is capital R. Okay, we just called e to the R capital R just for simplicity. And you have this lowercase r now is called the intrinsic rate of population growth. So think of it as like compound annual interest that accrues per unit time. Okay, so from now on, we're kind of dealing with this, right? We converted that power formula to this formula. They're identical, they're the same. Okay, so from here onwards, we're dealing with this R. Okay, that's great. So now, if you look at that formula, if R is positive, then the population is going to grow over time. In other words, there's more birth than there are deaths, right? So the net population is growing. Okay. Now, over time, R might change, right? And if R goes to 0, then you have no growth in the population. Okay, same number of birth, same number of death. Okay, and finally, if R is negative, then you're going to get a decay in the population, right? Because then there are more deaths than there are births. Okay, all right. Now, in reality, and this is the point that Nathan was making, okay, in reality, populations do not grow indefinitely and exponentially, because there is predation, there is resource limitation, right? There's competition. If you look at populations of rabbits and foxes and predator and prey models, they tend to oscillate over time. There is when rabbits, for example, start, and this would be an example in your homework, when rabbits can reproduce a lot, then that brings in their predators, foxes and wolves, and then that tends to reduce the population of the rabbits as the population of the wolves grow. But then as the population of rabbits decreases, then the wolves no longer have resources, so they start kind of dying off, and then the population of rabbits grows up. So there's always this balance in nature. But in practice, if you have limited, for example, predatory effect on the population, typically what we see in populations is that there's an initial growth that is exponential, and then eventually it reaches a plateau. Okay, I'm going to call that K over here. Technically, this is called the carrying capacity of a population. That's kind of the maximum a given population can reach. Okay. And initially, there's exponential growth, and then as the population increases, resources decrease. So there's a tendency to reach a balance between the environment and the population itself. And that K is called the carrying capacity of the population. Okay, so now I'm going to start. My objective is to derive a formula for this equation, for this curve. Okay, that's my objective. So now assume that due to food restrictions, a lobster population with intrinsic growth rate R cannot grow beyond K individuals. Okay, I want you to develop a formula for the population of lobsters as a function of time. So I want you to find that curve. How would you find that curve? So there's initial kind of growth, right? Just come up with a formula, right? And the answer could be like, I don't know how to come up with a formula like that. Okay. But I want you to try to think about it. How would you develop a formula for this system? This could be a reaction system, okay? And you're observing some new top secret chemical that's reacting in a certain way, right? And your objective is to develop an understanding of how that, solvent or that reactant reacts, right? Same thing. So how would you develop a formula for this? Okay. Something interesting going on there with that group was like nothing, right? So you wrote a derivative over here, kind of. I mean, you're on the right track, but we're going to get to that point. So what do you think? Can you just come up with a formula for this? I mean, think about the previous few questions, right? It was easy to come up with a formula. You just double the rate or whatever, multiply it, and then you can get R to the power T times P0, right? Could you do the same here? I don't know. I can't. The reality is that this is a very difficult problem to solve. This is the equation for this curve. Okay, this is the equation for this curve. Okay, let me show you. Initially, when time is very small, when time is very small, you're going to have exponential growth, or when P0, forget time, when P0, P0K, yes. So initially there is exponential growth, but then as the population reaches a certain time, so this is a function of time, as the population reaches a certain time, then this term essentially disappears because this becomes e to the minus infinity, right? As time increases, this becomes e to the minus infinity, and this term drops, and you get k, P0K over P0, which is k. Okay, but how the heck did I come up with this formula? And why is it true? Why is this formula true? Okay. So now we're going to use another approach. Rather than looking at the population itself, just like we did in the previous example when we said starting with P0, we're going to double P0 or multiply it by R and then keep multiplying by R. We were looking at the population value itself, P0, right? And P1 and P2. Rather than looking at the population value itself, what if we look at the rate of change of the population? How fast is that population changing over time? Okay, that rate of change. And the claim is it is going to be easier to come up with an equation that generates the formula than trying to get to the formula directly. Okay, so let's do a warm up a little bit. for a population, oops, why is this, should show, okay, yes. So consider a population of lobsters now with an initial size of P0, okay? The birth and death of lobsters is equal so that their population remains constant over time. So now I want you to develop an equation for the rate of change of P, the population P. So P0 is the initial condition, okay? We start off with P0, but the population is called P. So now develop an equation for the rate of change of P over time. So dP by dt for a population where birth and death are equal. So it's going to be dP by dt equals something. What is that thing for a population like this? So what does it mean when there's no net growth in the population? What does it mean on its rate of change? Correct. So we got the answer. Okay. So what this means is, excuse me, for a population with no net growth or no net shrinking, there's no change. There's no change. dP by dt is identically equal to 0. Correct? And then the answer to that, if you solve that exactly, you get P of t equal to a constant. And because the initial population is P0, that constant is P0. So that population does not change. Okay. All right. So now take that same population, okay, starting with P0, and assume now that it is changing at the rate R. Okay. So now your rate of change of the lobsters, okay, is that intrinsic population growth is R. But remember, the more lobsters that you have, the more likely they are gonna reproduce, right? Okay. So effectively, if you have 10 lobsters, so that's R times 10. If you have 1,000, that's R times 1,000, because there's more likelihood of more of them, reproducing, right? So now develop an equation for the rate of change, okay, for the population P, where they're growing by a rate R, so that R times P new lobsters are added or removed per unit time. Okay, so that's the net change in the lobster population, okay, per unit time. So now come up with a differential equation for a population like that. dP by dt, is it equal R? Is it equal RP? Is it equal R minus RP? Oh, you're okay. Okay. I know these examples might seem elementary, but they're gonna get clearer. Okay. Yeah, just ask yourself, what is the at a given state in the population, how many new lobsters are going to come up at a given state of the population? It could be 10 lobsters, 1,000 lobsters. How many new lobsters are going to come up in the next unit of time? That is your rate of change. Yeah, so yes, this is correct, but this is the answer, right? Yeah, but this is correct because now you're relating the rate of change of P to P itself, right? So this would be the answer to that. Okay. All right. So do I have any answers? Rich? Correct. Okay. Who got that answer? Okay. Who got another model, another answer? Some answers I've had were dp by dt equal r. Okay, and that's not wrong. That's just one model, but that means if you put dp by dt equal r, that means your population is only changing by a fixed number, whether there's 1,000,000 lobsters or 2 lobsters. They're always making 1 lobster, every day, right? But that's not very realistic. Realistically, if r is equal to 1, let's say, or 2 or 1.3, right? The more lobsters you have, the more that they're gonna reproduce. Okay. So the rate of change of the population will be equal to the change of population itself, RP. So therefore, your differential equation is dP by dt equal R times P. Okay, because now we're starting to think in terms of rate of change. Now the solution to this equation is a constant times e to the RT, and that constant at t equals 0 is P0. So it gives you P equal P0 e to the RT, exactly the answer that we obtained, okay, by hand previously. You might say that the previous method was easier. I agree. But once you get to the population that goes to a plateau, then this method is going to be more superior. And that's going to be our next challenge. So now we're going to use that same methodology, looking at the rate of change of the population. We know it's kind of growing at RP over here, okay? The rate of change is RP. It's exponential growth initially, right? But there's a point at which the rate of change essentially goes to 0, right? So your right-hand side for the differential equation needs to have some sort of a continuous switch where it's initially growing exponentially, but then when the population reaches K, the rate of change becomes 0. Okay, so I'm going to suggest you do something like this. Where you have a switch. If you had R times P, then your population is going to grow exponentially. But we need to make that right-hand side to go to 0. So we need to kind of adjust that right-hand side a little bit, such that when the population P is equal to 0, the right-hand side goes to 0. So that it doesn't change anymore, right? So when you think about the slope of this curve, initially it's growing exponentially. dP by dt is R times P. But then after the population reaches K, dP by dt is 0, exactly 0, right? It doesn't change anymore. It kind of flattens out. So I gave you a little hint here to change that R to R times some switch, okay? Because that is going to be your switch here. I think whatever course that's teaching ODEs should teach how you build ODEs, okay? So we're going to get a chance to build a few ODEs together, okay? But this is just kind of a little peek at that, right? Because this is very powerful. This is going to allow you to make models, to invent models for systems that you're observing, okay? This kind of thinking, this kind of analysis. So now think about it. Our rate of change needs a switch such that when the population reaches K, it doesn't grow anymore. Okay, so when P is equal to K, then the entire right-hand side is 0. But yet you're still thinking in terms of dP by dt, okay? What do you think, Nathan? Okay, why? So Nathan is saying, sorry to interrupt you, Nathan is saying we replace this question mark with K, the carrying capacity of the population. Go ahead.
Yeah, because
So as P approaches K, yeah, so then when P approaches K, then K minus P becomes a very small number, therefore driving the right-hand side to 0, and therefore reaching this dP by dt equals 0, which we showed in the first example, right? When dP by dt equal to 0, there's no change. But what happens initially when P is very small? Yeah, right, because K is going to dominate. When P is very small, when we're starting off, when P is small compared to K, then K is going to dominate, right? So that term is very positive, very far away from 0, okay? And it is going to dominate. So that's the correct answer, okay? So if we start with dP by dt equal Rp, what I'm suggesting is that we replace R by this switch, R times K minus P. Now that switch is going to tell us that as P approaches K, then this becomes 0. And it accomplishes what we need to accomplish. Otherwise, it's going to give us some form of exponential growth. And the exact solution, to this equation is the one I showed you before: P0 times K over P0 plus K minus P0 e to the minus RT. And that's how I obtained that equation, okay? So we looked at the rate of change in the population. We developed a differential equation that governs the population growth. And we were able to use that to derive the formula for that population growth. So this leads us to the following definitions and observations. Despite the fact that you might have thought of this as a little bit, at least that last problem, like, yeah, it wasn't very intuitive, but it is one step easier than coming up with the formula for that population growing and then plateauing, because now you have at least a tool. Look, we cannot figure out the formula for that system. How about we develop a differential equation for that system? And now you start thinking, okay, what is the rate of change and how does it grow? I want it to go to 0 when it goes over there. So you have something to work with. You have a better toolbox than just coming up with a formula, out of thin air, okay? Now, very importantly is this observation. The solution of a differential equation is a function, okay? Is a function that you use to get a number. But then the solution of an algebraic formula on an algebraic equation is just a number. So you've just created a whole level of complexity and wealth and breadth and depth in your ability to analyze systems, because the differential equation is not going to give you just one number as an answer. It's actually a formula generating formula, right? That equation generates formulas, right? And this is mind-blowing. It's a methodology to come up with formulas, right? It's brilliant. It's brilliant, right? You don't have to deal with the quantities anymore and think like, what is my formula? Just come up with a differential equation, find a general formula and give it to others to use it, right? So that is the power of differential equations. They are formula generating equations, right? Rather than when you take the formula, you apply it, you get just one number, right? But the differential equation can give you the formula for any condition. You change R, you change T, etc. You can change the rates of change. You come up with different formulas, okay? And I try to describe this. The function that results from the solution of a differential equation serves as the algebraic relation that someone can use to make predictions and get specific predictions with specific numerical values. So now I want you to just list some examples from daily life about things, about rates of change, okay? So now change your thinking about things. You spend, on average $10 a day or whatever on lunch and food. Right now, think of it as a rate of change. What is your rate of spending per day or per month or per year, okay? What is your rate of saving? Rather than saying, I saved, $100 this month. What is your rate of saving out of, all of the jobs you have? Think of examples of rates of change, okay? in daily life, the rate of change of something. Okay, not the magnitude, the rate of change, the rate of usage of something, the rate of spending of something. Okay, give me some examples from daily life. So I'll give you an example. During COVID, I developed a formula for the rate of change of our laundry detergent usage. Okay, so that I could predict how many, that was like pre-shutdown, how many gallons of laundry detergent I had to buy. Okay, because it changes, with winter and the summer, there's like, in the summer there you're using much more clothes with the kids, everything, there's water and mud on everything. But then in the winter, if they're outside in snow, you have these, the snowsuit and like the big thicker clothes. So, it changes. So we ended up getting as many as we needed. Some of them went bad, but we didn't use them. But, things like that. All right, some examples. What are you thinking? There's no rates of change. Everything. You guys say what?
I was gonna say food. I always buy like a huge thing of minute rice.
I love that minute rice, right? Yeah, yeah. Okay. Kevin, team, no? Okay. Yep. Correct. Okay. What about you? Okay, so let me ask you this: is the right-hand side positive or negative? Is the amount of knowledge increasing? Hopefully, I should. Maxime.
Well, I was going to say, as the lecture goes on,
the rate of knowledge gain goes down. Why?
Because
Oh, but that's why we have these activities, right? So to kind of break that monotonic structure. Okay. Nathan,
I have one.
your resting heart rate. Okay. Rate of change of gas prices is a very good example. Okay. Liz, Hannah, you got something? Some rate of change of something? Yeah, sure. Yep, exactly. What about you guys? You have an example?
I have the change in the amount of money I spend as a function of the change in the amount of time I spend with friends.
All right. What about you? Gas prices. Yeah, drive. Yep. That's right, Ryan.
We also did like the
Temperature the day. Okay. Team over there.
The flow of electricity through power cables, your computer's charging.
Okay. Yep. All rates of change. Okay. You'd be surprised what things you can, when you're looking at your living situation, everything in your daily life, if you start, rather than thinking about the actual amount of something that you're spending on or you're using, like how many miles you're driving a year to come to school, think about the rate of change of that throughout the year. So first maybe plot it, and then think about it in a different way. You might come up with an actual model. So these are some examples from things from previous years. Clearly during the pandemic, when I developed these slides, everyone was saying about rate of infection, rate of people, going to the hospital, etc., rate of interest on a loan, rate of growth of your investments and whatnot. Anyway, okay. All right, great. So I'll give you a 2-minute break because, I was just told that the rate of information gain is decreasing. So maybe now you can go and recharge so that we can make that positive. Okay. So take 2 minutes and then we'll continue. Okay. Gonna resume recording. We'll be back to differential equations. Now we're going to classify. We only talked about differential equations now. Those could be ODEs or PDEs. I gave the example of ODEs because they're simpler to deal with, but differential equations, they cover both ODEs and PDEs. And this is what's on this next slide. They're generally divided into ordinary and partial. An ordinary differential equation is a differential equation, so it has derivatives in it, okay, of the function. But it usually always has a single independent variable, x or t, so only has one dimension in it, okay? That's what makes it ordinary. What that means, what that implies is that the derivatives are ordinary derivatives. So the letter D, the symbol D, okay? Not partial, not del, the symbol D. So that's the symbol for an ordinary derivative, and that's why we call those ordinary differential equations. There's, you know, they can be very extraordinary, okay, with complexity, but we call them ordinary because of the presence of ordinary derivatives. And, you know, some examples is this population growth with the carrying capacity K, the rate of change of height of water in a tank, for example. You're filling a tank with some flow rate coming in, flow rate coming out over the area of the tank or the bucket. And advection diffusion equation. So this has to do with fluid flow and heat transfer as well. And just simply a reaction system, okay? On the other hand, a partial differential equation is a differential equation with one or more independent variables, x, y, z, and t. You could have all of those combined together, okay? Regardless of the order of the derivative, second, first order, it doesn't matter. They're all, you know, differential equations. So for example, this is a steady state heat transfer equation, also called the Laplace equation. This is an unsteady heat diffusion equation. This is the unsteady advection diffusion equation, both in time and space. So, you know, there's the classic example for this. I'll show it on the next slide. But, you know, this is something where you are heating something and it is both diffusing and there is some, you know, some air blowing at it or some fluid kind of immersed in the system that is moving changing the temperature, moving it around, okay? Examples of ODEs and PDEs. Okay, so that's the classification of differential equations. We are going to focus on this side, okay, on ordinary differential equations, and we're going to classify those as well, okay? If you've noticed in the previous slide, there are equations that have t in them, and some of them have x, right? So some of them have time, some of them have space. Okay, there's a distinction between those two, and that leads us to classify ODEs. We classify ODEs into two types of problems: initial value problems and boundary value problems, okay? Initial value problems, we also call them propagation problems. So essentially, given the state of a system at an initial condition, at some time, you call that T0, okay? How does that system evolve in time according to the rules of the ordinary differential equation, okay? This is a classic problem in reacting systems. So like well-mixed reactors, you're filling and emptying a tank, for example, population growth that we saw, pandemic, disease spread, etc. Things starting with an initial state, and they are changing over time, subject to conditions that also could change over time. Infection rates, for example, for a pandemic, etc. Okay. On the other hand, boundary value problems, also called equilibrium problems, is because you are given the state of the system only at the boundaries, and you are asked about what happens inside that system. Okay. Now, there is a possibility for things to change over time, but when you add a time derivative, that becomes a PDE. If you remove the time derivative, then it just becomes an ODE. So the example is the heated rod we did early on in class, where we fix the temperatures of the rod on both sides, right? And ask the question, what is the temperature inside the rod? Okay, what is the temperature distribution inside the rod? In this room, okay, I open the door over there and I close it over here, and there's ventilation. I specified the conditions along the boundary. What does the airflow look like in this room? Okay, that's a boundary value equilibrium problem. The classic problem we use as an example for this is heat transfer. This is your wall. You got the sheetrock outside, some insulation, some plywood, and some siding. So, sorry, this is the outside siding, plywood, insulation, and your sheetrock. This is the inside. And you want to understand if the temperature outside drops 10 degrees and you're trying to maintain a temperature at 70 inside, what does the heat transfer look like throughout this? That's an equilibrium problem. You fix the temperatures on both ends and tell me what's going on inside that wall, right? Because that could help us determine the thickness of the insulation, what type of insulation we use, the thickness of the plywood, and so on. Okay. Okay, great. Right. I give a bunch of other examples. Okay. So as the name indicates, initial value problems only require an initial condition, but boundary value problems require boundary conditions. Okay. Now, when you think initial value, when you see time in an ODE, when you see T in an ODE, you should immediately conclude that this is an initial value problem. Okay. 99.99% of the world uses T as the symbol for time in differential equations. So you should be pretty reassured that when you see an ODE with T as an independent variable, that's an initial value problem. Okay. When you see X or Y or something else or Z or Q or whatever, that's probably a boundary value problem. Okay. We continue with the classification. We say that a first order ODE contains only the first derivative of a dependent variable. You could have a single equation. So d phi by dt equals some right-hand side. So from now on, we're going to call our ODEs as d phi by dt equals some right-hand side. This is not the population growth. We're done with population growth. Okay. This R is a full right-hand side. It could be a function of time, the independent variable, and phi itself. Okay. It's just a general right-hand side. We're going to call that the right-hand side or the forcing function. Some of you might have seen that word. Okay. This is also another first order ODE. The first one is probably an initial value problem. The second one is a boundary value problem. But both of these equations are first order ODEs. Now, the same way we had systems of linear equations and systems of nonlinear equations, you could have systems of ODEs. Why? Because ODEs can be coupled to each other. You have two competing reagents reacting with each other, producing a product. You're going to have three equations, or at least two equations there, okay, that are tied into each other, because the first equation is going to depend on the value of the second, and the second is going to depend on the value of the first, right? So we write this then as d phi by dt equals some right-hand side of t and phi, but phi now is a vector of variables. So d phi 1 by dt is r of t and a function of all the other variables. And then d phi 2 by dt, d phi 3 by dt, and their right-hand sides could be a function of themselves or only one other variable or all the other variables. This is the most generic form. Okay. Same thing for a boundary value problem, but those are all first order ordinary differential equations. Now, a second order ODE is one that contains at most second order derivatives, but it could also contain first order derivatives. Okay. Such is the example of the advection diffusion equation. Okay. You will later learn the physics of this equation. I'll just kind of expose you a little bit to it. So whenever you see a second derivative in space, that means diffusion. Diffusion is a process where information could be temperature, could be concentration, okay, is communicated at the molecular level due to vibration of the molecules. I'm vibrating, you know, everyone else needs to vibrate next to me, right? So that's what diffusion is doing, okay? It's communicating information at the molecular level. Convection, however, is always associated with a first derivative multiplied by a speed, a gas speed or a fluid speed, because convection happens more at the macroscopic scale, you need wind to move things around, okay? So if you had a stick of incense and you kind of let it flow around, it's kind of being more or less advected by the slightly heated tip of the incense stick. Then you put a fan on it, your neighbor is going to come out screaming, what is that incense? You're burning. Why? Because they smelled it, right? Because the air moved that incense smell immediately to them much faster, okay? Right? So that's UDC by dx over here, okay? And I like to give this classic example, right? Of the, apple pie being cooked and, Mickey Mouse smells it and, follows the trail, right? That's kind of an example of an advection diffusion system, okay? Now, what is an example of a system of ODEs? And we're gonna drill into this example, do this example together in class. It's a model for pandemics. It's called the SIR model, susceptible, infected, and recovered. And we will be able to together derive these equations for this system. But this system assumes that in any epidemic, which eventually turns into a pandemic, there are three types of individuals. There are those who are susceptible to be infected, right? They are the healthy, uninfected individuals, okay? And there are some of them infected. Maybe one person, came in, they brought the illness with them. And so as there's interaction between the susceptible, the uninfected with the infected, then the rate of infected goes up as the rate of susceptible go down, because susceptible people are now becoming infected. Now, after a certain amount of time, the infected, so we go from blue to red, and then from red, we go to green because they become immune and recovered. And this is the balance of what happens in a pandemic. When we say we want to flatten the curve, our objective is, to make that peak reach a certain level. Does not go above a certain level, because hospital capacity, etc., they have a certain number of infected individuals that they could treat, right? And so when the question is, how do you flatten the curve? It's essentially, this is a very simplified model of that, but it's pretty darn good. And 2 years ago, together, we also derived one where we included the effect of social distancing. Okay, we developed a model on social distancing. We're not going to cover it this year, but I'll keep it in the slides at the end if you're interested in looking at it. But it's a pretty darn good representation of what happens in a pandemic. You have susceptible individuals, you bring in one infected individual, and as they interact with each other, there's more infected interact with more susceptible, some infected become recovered, and eventually when you have essentially full immunity, okay? We'll derive this system together, but ODEs are pretty powerful, okay? This is a very popular model, and what they use actually to do predictions at the CDC is no different than this, except that the coefficients are not constant. They are derived from actual data that continuously kind of updated. But this is the basis of that kind of modeling. Okay. So finally, okay, why should we use numerical methods to solve ODEs? It's the same story over and over again. It's because for most systems, the differential equations that govern those systems are nonlinear coupled, and it's, impossible to find analytical solutions to those, to find the formula that we want to apply. But despite that fact, the numerical method is going to allow us to find instances of that formula under different conditions, okay? So in other words, the numerical method is going to allow us to find a surrogate for that formula, a numerical surrogate for that formula, okay? And hence, there's an immediate need to study how one can solve. I don't know how immediate it is, but there's a need to study how we can solve differential equations numerically, okay? All right, so we are going to start with doing initial value problems, okay? I should have given the break right now, actually, rather than 10 minutes ago, but okay. So we're going to start solving initial value problems. We're going to spend a good portion of time on initial value problems, and we're going to learn how to do it in Python first, using a built-in function in Python, and then we'll learn what goes on under the hood, okay? So for initial value problems, we are looking at equations of the form d phi by dt equals some right-hand side, that's a function of t and phi, with an initial condition, phi at 0 is equal to phi 0. Phi is just a dummy variable. Could be temperature, could be pressure, could be concentration. Anything is just phi. Okay. So by now, that I hope should be clear. All right. So we are gonna cook a lobster. Okay. Don't ask me about my obsession with lobsters, but like I've actually had one lobster in my entire life. That was in Tennessee, but there's a very historical precedent for why I'm using lobsters. But if you're a vegetarian, don't like lobsters, for the rest of the exercise, you can substitute the lobster with an eggplant or a zucchini or something, because it's the same idea. We're gonna try to look at how we are gonna cook the lobster. Please stop laughing. Okay. Okay. All right. So we're gonna make up a story now, because it's fun and kind of tends to drive the point home. And apparently, a recent report that was completely made up found that the population of lobsters is growing out of hand, and that those lobsters are essentially eating everything at the ocean floor, and they're destroying the global ecosystem, and it's like hurricanes and crazy things going on. So, the WHO and the CDC are recommending that people start eating lobsters a lot, like snacks, in the car, whatever, lobster croissants, I guess, or, with your eggs, everything, just to control the lobster population, okay? And as a chemical engineer, you are tasked with finding out the fastest method that you could cook a lobster, okay? And you have two options, either boiling it in a liquid, like water, oil, your air fryer, for example, right? I recently acquired an air fryer, and it's a great excuse to make a lot of French fries because they're healthy, right? And so the question is, okay, is it faster to boil it or bake it in the oven in radiation, right? In the oven, it's a radiation environment primarily. There's some kind of convection, right, going on, but it's mostly radiation from the heating elements, right? But so which one is faster? And also, which one is faster in boiling it? Should you use water or oil or an air fryer, right? So you are tasked with answering those questions, okay? So we're gonna do, pardon me? What was that? Okay, all right. So we're gonna make some assumptions. We're gonna assume that the lobster is a cylinder, okay, of length L. Right, that's kind of the first. It's like the first thing that a physicist does. Assume the chicken is a sphere, and so okay. So a lobster is a cylinder of, on average length, 30 centimeters and about 10 centimeters in radius, Mr. Lobster. And we're going to assume that the lobster throughout the cooking, okay, remains at the same temperature. Why did I say that? Because I want to make this an ODE. If I allowed the temperature to change internally, then it's changing in time and in space across the eggplant or the lobster, right? So I don't want that. I want to assume that the entire lobster or the eggplant remain at the same temperature, okay, so that I can make this an ODE, okay? So that's kind of my second assumption, all right? And then that the lobster's mass remains constant with time, fairly good assumption. And that the heat capacity of the lobster is approximately that of water. That's a very reasonable assumption. Lobster is like 70% water. It lives its whole life in water. I mean, it's probably more than that in water. But, so that's important when you're thinking about heat transfer. Might not be very relevant to you right now, but, those are the assumptions that allow us to use the model that I'm going to propose. These are some numbers we're going to be using. The length of the lobster is 30 centimeters, radius is 10 centimeters. The area is, the total surface area is this, because we're exposing the surface of the lobster to either the radiative environment or the boiling water or heated air or oil. The mass is 1 kilogram, and the heat capacity is 4,200 joules per kilogram Kelvin, okay? So those are just numbers that we're gonna punch in to get to our models. Now, in this class, I'm not gonna teach you how to derive those models, although I hope that what we covered so far about rates of change kind of gave you an idea, hopefully next time when you do heat transfer course, like, oh, I remember these lectures of how we create ODEs, thinking about rates of change. But now I'm gonna give you the ODEs, okay? So when you boil it in water, it's called a convective heat transfer process. The temperature of the lobster is changing in time. The rate of change of the temperature as a function of time. And that is going to be affected by the temperature of the fluid, right? Minus the temperature of the lobster itself. Clearly, when the lobster, so think about the population with the carrying capacity, okay? When the lobster's temperature reaches the temperature of the fluid, there's no more heating taking place. There's no more cooking. We're done, all right? However, when the initial temperature of the lobster is far away from the temperature of the fluid, then there's a lot of heating going on, okay? So you could imagine the lobster is going to heat up initially, maybe linearly, and then kind of plateau. Now, these coefficients over here, the A, M, and CP, they have to do with the properties of the lobster. We're going to assume that they are fixed, this A over MCP, they're constant, but this H is a parameter that we're going to manipulate, because this tells us whether you're heating it in water, in oil, or in air. It's called the heat transfer coefficient. Okay, so let me ask you this. Would you rather put your hand on, like, you know, warm air or warm water or warm oil? Right? Yeah, air, because it has a lower heat transfer coefficient. Okay, whereas water can heat things faster and oil even faster. Right? That's why you cook in oil. Okay, because the heat transfer coefficient of oil is much higher than the heat transfer coefficient of, I think Nathan is fact checking me, than the heat transfer coefficient of water. Okay, so, and that's how we're going to change our cooking fluid. Okay, but note also, which you can change two things. While water boils at 100 degrees and has a higher heat transfer coefficient, your air fryer can get the air to a much higher temperature, but at a lower heat transfer coefficient. Okay, so we can look at those things and see how the heat in the lobster, how the cooking of the lobster occurs. Okay, now baking it in the oven in a radiative heat transfer environment, you still have the rate of change of temperature of the lobster. This is the entire lobster, its entire temperature, how it's changing over time. But in a radiative environment, you have the temperature, it looks like that equation, right? Except that the temperature is to the power 4. So that effect is, is exponentially increased when you have radiation. T infinity is the radiative temperature environment. You put your oven at 350, for example. Okay, this gets T 350 to the power 4. And then your current lobster temperature, remember, T is changing over time. So this value is also changing over time, right? Again, as T reaches T infinity, you're going to plateau. You've cooked the lobster, you're done. Okay, but if T is lower, there's a huge gradient here. So it's going to keep heating and adding to this dT by dt. Okay. Now, these are constants over here. Emissivity and sigma and A and MCP, they're all constants. So all we can change here is either, you know, bake it or broil it or whatever, changing that T infinity. Okay. Okay. So we're not gonna, first we're gonna solve this problem using Python. Okay. But I need some numerical ingredients, okay, to show you what we need so that we can do it in Python. Unfortunately, I feel like I'm going to finish before we actually do it in Python. So we might have to repeat these last few slides next Tuesday, but that's okay. Okay. So to solve an ODE, d phi by dt equals some right-hand side with an initial condition phi at t equals 0 equal phi 0, starting from t0 to an end time, because you have to specify that, like how far in time are you integrating, are you solving that differential equation, that ordinary differential equation. So what we do, just like we did with the rod, we're going to take the time interval from t0 to t end, okay, starting with the initial condition of phi. So our purpose is to find this curve. This is the solution for the differential equation. So what we're going to do, what we did with the rod. We're going to divide the time interval here rather than the space interval. We're going to divide it into what we call time steps. Okay, just T1, T2, T3, all the way to T end with a fixed spacing delta T. That's the simplest we can do. Don't worry about, you can make delta T not constant. That's not a worry. Right now, we assume you divide that time interval into discrete times. And then your objective would be to find the discrete values of phi, right? Because we're solving it numerically. So we're going to create an array of time intervals starting from t0 to t end with a specific time interval. And then the ODE numerical solution is going to go ahead and proceed to find phi1, phi2, starting with phi0 is going to predict phi1, and then using phi1 is going to predict phi2, and so on and so forth. Okay. And we'll understand how to do that, but first we're going to do it in Python. Okay. So scipy.integrate provides a library for solving ODEs in general called ODE-int, same as in MATLAB if you've used that in MATLAB. So thankfully, we can use the same nomenclature in Python as well. ODE-int solves an ODE of the form d phi by dt equal right-hand side. Now notice the right-hand side function. The default function in Python is a right-hand side function with the arguments in this specific order, phi and t, not t and phi. So when you define your right-hand side function to give it to ODE-int, you better make sure that your arguments, your first argument is phi, and your second argument is time. Okay, so that when inside the right-hand side you build the right-hand side to use phi and t, make sure you use those correctly. Okay, and this is what it looks like. ODE-int, right-hand side, initial condition, and your time array, and a bunch of optional arguments. But this is the minimum that you need: a right-hand side function, an initial condition, and a time t. So let me show you more details. The right-hand side is simply a Python routine, okay, that implements the right-hand side of the ODE given phi and t. So you're assumed that you know phi and t. Think of the Jacobian we implemented just last Tuesday, right? We implemented the Jacobian. We assumed that the Jacobian takes a bunch of arguments, and our Newton solver or our fsolve, excuse me, the residual function, sorry, the residual function, right? It had specific arguments that fsolve always called that residual function with those arguments. So you're going to assume that ODE-int is going to call the right-hand side routine, but that routine should take phi and t as arguments, okay, in that order, in that specific order, okay? Phi0 is your initial condition, and t is simply an array or a sequence of time points at which you want to solve for phi. So those are your t0, t1, t2. You could have them equally spaced, unequally spaced. ODE-int will figure that out. Okay, just give it essentially a numpy.lin space. Okay, and finally, okay, so this is how you define your right-hand side. So your right-hand side, you pass it the name of this function, but your function is defined right-hand side phi t, and inside it you use phi as if you know what phi is, and you use t as if you know what t is. ODE-int is going to call this right-hand side and give it the correct phi and the correct t at the time it's integrating. Okay, don't worry about how it's doing that. Okay, we will get to do that ourselves. Okay, and finally, when you solve this, ODE-int is going to return an array that contains your numerical solution, phi at t0, phi at t1, phi at t2, and so on all the way to phi at t end. Okay, that's what it does. It's great routine, works most of the time for initial value problems. Okay, I don't have time to do the example actually together today, so I will let you go now. But on Tuesday, if you don't mind, we'll start a couple of minutes earlier because we are really kind of tight on time from now to the end of the semester. So if you could come a couple of minutes earlier, please, that'd be great. We'll start on the example immediately. Okay, and after we do ODE-int, okay, we're gonna learn how we derive what's inside ODE-int. Okay, all right, have a nice weekend. Thank you. On Zoom, any questions on Zoom?